This video is on section 9.4 notes, inverses of matrices. So I want to review a few things with you before we move on to matrices. The first is to discuss what a multiplicative identity is. The multiplicative identity of a number, because numbers are the easiest thing for us to talk about, but this would work with an expression or a matrix or a function or whatever else we talk about in math. But the multiplicative identity of a number is whatever you can multiply the number by so that it remains unchanged. So the multiplicative identity for any number is just 1. If I multiply any number by 1, I just get the number itself. So that's the multiplicative identity. The additive identity of a number, or matrix or function or expression or whatever, is whatever you can add to a number so that it remains unchanged. So the additive identity for numbers is 0. I can always add 0 to a number and that number is going to stay looking the way that it does. And then I just want to remind you that an inverse operation is an operation which will undo another operation. So we've learned about lots of inverses at this point in our math careers. Adding and subtracting are inverse operations. Multiplying and dividing are inverse operations. Squaring and square rooting. Logging a number or raising a number to an exponent. The exponent, anyway. Logs and exponential functions are opposites of each other, that sort of thing. So now we're going to move on and talk about matrices. And first we're going to talk about the multiplicative identity matrix, which means we're going to look at what matrix you can multiply another matrix by and just end up with the original matrix. So first, we have I2, which is a 2 by 2 identity matrix. We have I3, which is a 3 by 3 identity matrix. And the identity matrices always have to be square matrices. So this first one is 1, 0, 0, 1. So you have to have 1s on this diagonal. For 3, it's 1, 0, 0, 0, 1, 0, 0, 0, 1. So you've got 1s along the diagonal, 0s everywhere else. You could write a 4 by 4 matrix and do the same thing and just have 1s along the diagonal and 0s everywhere else. So what I'm going to do next is I'm going to multiply matrix A by its identity matrix, just to prove to you that if I multiply A by the identity, I'm just going to get A, because it's the multiplicative identity. It doesn't change the number, it doesn't change the matrix, it keeps it the same. So I'm going to do A times the identity first. So 2, -7, 5, 6, multiplied by 1, 0, 0, 1. Okay, and so when I multiply, my left finger goes across the row, my right finger goes down the column. So 2 plus 0 is just 2. 0 minus 7 is just -7. 5 plus 0 is 5. 0 plus 6 is 6. So there you can see, if I take a matrix and multiply it by the identity, I just get the original matrix. Next, I'm going to take the identity and multiply it by the matrix itself, because we know that matrices can have different products if you change their order. So we just want to prove that when you multiply a matrix by the identity, the multiplicative identity, that it doesn't matter the order, you're going to get the same result no matter what. So again, I'm going to multiply these. 2 plus 0 is 2. -7 plus 0 is -7. 0 plus 5 is 5. And 0 plus 6 is 6. So no matter which order we do it, we're going to get the original matrix. Okay, so there's the multiplicative identity. You'll see a little bit later on in the notes where that's useful, but it's good for us to know that. Okay, next we're going to talk about inverses and the identity matrix. So we want to see how to find inverses, what their usefulness is, and how they interact with the identity matrix. So this says that if we have A and B, to find the product A times B and find the product B times A. So A times B, 3, 4, 5, 7. And 7, -4, -5, 3. So it's a 2 by 2 matrix times a 2 by 2 matrix. So our result is going to be a 2 by 2 matrix. All right, so we've got 21 minus 20. That gives us 1. Then we've got -12 plus 12, which gives us 0. 35 minus 35 gives us 0. -20 plus 21 gives us 1. So when we multiplied A and B, we got the identity matrix. All right, now I'm going to multiply B times A. So 7, -4, -5, 3. 3, 4, 5, 7. Okay, and again, I'm going to get a 2 by 2. That's the answer. All right. So this is 21 minus 20. 28 minus 28. -15 plus 15. -20 plus 21. So A times B is the identity matrix, B times A is the identity matrix, excuse me. So in both of these cases, we can see that essentially what happened is these two matrices kind of like canceled each other out and got us back to the identity. Something kind of weird happened there. So let's look at the next page and see what happens in this page of notes. It gives us a 3 by 3 matrix and another 3 by 3 matrix and wants us to do the same thing again. Find AB, find BA. So I'm going to go ahead and find AB. And a 3 by 3 matrix multiplied by another 3 by 3 matrix gives us the result of a 3 by 3 matrix. Okay, so -1, 0, 2 gives us 1. -2, 0, 2 gives us 0. 2, 0, -2 gives us 0. 2, -3, 1 gives us 0. 4, -4, 1 gives us 1. -4, 5, -1 gives us 0. 1, -3, 2 gives us 0. 2, -4, 2 gives us 0. -2, 5, -2 gives us 1. So we got the identity. Okay, so -1, 4, -2. It's 1, 0, -2, +2 is 0, -2, -2, 4 is 0, -3, +8, -5, 0, 0, -4, +5 is 1, -6, -4, +10, 1, -2, +1, 0, 0, 1, -1, 2, 1, -2. Okay, so if you have this situation where A times B, they cancel each other out, you get the identity, and then B times A, they cancel each other out, you get the identity. Matrix A and matrix B must be two matrices that undo each other, which means they must be inverses. So on the previous page, these two matrices are inverses of each other. That's why they cancel each other out and give you the identity. These two matrices are inverses of each other. That's why they cancel each other out and give you the identity when you multiply them. All right, so what we want to do next is look at how to find an inverse matrix. So if you are given matrix A, and the elements of matrix A are A, B, C, and D, the first thing you need to do is find the determinant of A. And the determinant of A is AD minus BC. Okay, so AD minus BC. So I'm going to give you 3 different examples, and we're going to find the determinant first, and then we're going to go through and finish finding the inverse. So for this one, we've got AD is 15 minus B times C, -2. So this determinant is 17. Here our determinant is -9 minus -6. Here our determinant is 10 minus -3 is 13. Forgot to write the answer here. -9 plus 6 is -3. Okay, so there's our 3 determinants for the first 3 examples of inverses we're going to find. Okay, so now we're going back to the first one. We know the determinant is 17. So if the determinant is not 0, this doesn't work if the determinant is 0, then the inverse of matrix A, also known as A inverse, is 1 divided by the determinant, and then you have to do this to the matrix. So A and D switch places, B and C switch signs, okay? So I'm going to write A inverse is 1 over the determinant. So we found 17 for this first one. A and D switch places. B and C switch signs. So 5, 3, +1, -2. And this 1 over determinant is just a scalar for scalar multiplication. And so I can go ahead and multiply by each of those numbers in there. So the inverse matrix is 5 over 17, 1 over 17, -2 over 17, and 3 over 17. And because of the formula for finding an inverse matrix, because it's 1 over determinant times this, you'll find that usually your inverse matrices are fractions. All the elements inside of them are fractions. At the beginning of these notes, with those examples here where I have these two are inverses and give you the identity, the fact that these are inverses of each other, but neither one of them has fractions is very unique. It means that the people who came up with this example in the book, they did a very good job of finding matrices that didn't need fractions, but it's not very common. It's not often that you run into an inverse that doesn't have fractions in it. Because of this formula, you often have fractions in your inverse matrix. So if you do end up with fractions, you can feel good about that. You can feel comfortable. It does not mean you did something wrong. Okay, let's move on to the next one. So next we're going to take this matrix right here and we're going to use this as the determinant so we can find the inverse. So the determinant for this one was -3. So the inverse is 1 divided by -3. And then we have to switch A and D and change the sign for B and C. So 3 and -3, switch the order, change the sign. And then I can go through and do that scalar multiplication. So 3 times -1/3 is -1. -6 times -1/3 is +2. 1 times -1/3 is -1/3. And -3 times -1/3 is +1. All right, and then we'll do this last one, 1 over determinant. Trade positions for those two, change the sign. So 5, 2, 1, -3. And then we're going to multiply by 1/13. So 5 over 13, 1 over 13, -3 over 13, 2 over 13 is our inverse matrix.